All right, we're going to be talking about volumes with known cross sections. So I'm in a GeoGebra page here, and let me show you what I'm looking at. What we have at the is two different functions. Let me get rid of one of them. This is a part of a parabola, and this is actually a 3D grid here. You see it moving around, and we're only showing the parabola from A to B, so I can change the value to A. Then I'm looking at this tricky trig function here, right? There it is there. And again, showing it from -8 to 9. Oops, now it's going off on its own. Crazy. All right, let me put the upper function back. Okay, so we're looking at those two functions bound between -8 and 9. Okay, and of course I can change those bounds like so. What we're looking at then, if we think about this as being we're looking down at it from the top, like we are on the ceiling, or this is like Google Earth view, right? We're looking straight down from the top. And we're trying to see, there's going to be a three-dimensional shape. So this is the floor of our three-dimensional shape. Let me fill it in a bit. And then this is like the street view. Okay, so Google Earth view, street view. Okay, we got a three-dimensional shape. We want to find the volume of it. You see there's a little right triangle there. Let me explain what that is. Let me unfill this. Okay, so here's my floor. And what we're doing is we are taking right triangles and we're putting them parallel, this one that says up here, right triangles, cross section parallel to the y-axis, okay? Sometimes it says perpendicular to the x-axis, but it's the same thing. And so you can see that little right triangle right there, and then we have an isosceles right triangle right here. So it's isosceles, so you can see the right angle is marked. So that leg that's going up and that leg, of course, are congruent, and then you got the hypotenuse coming off in that direction. So if you're looking at, for example, if we slide this distance right here at where x is 0, is much bigger than this distance right here. So it would make sense that that triangle there in the middle is going to be much taller than the triangle that's way over here, where the distance between the two functions is shorter, okay, because the triangle is smaller. Okay, the idea is that we're going to have an infinite number of triangles that are infinitely thin, and it's going to make this 3D solid, and we're going to find the volume of it. Let me show you another one. Here we have the upper function is this trig function. If I get rid of this one, you'll be able to see it. There it is, just a basic trig function. And then we have my other function is this line, this slant line right here, 0.2x minus 5. And we're bound between -7 and -8, or sorry, -7 and +8. So we can see the bounds change as so. And this time our cross sections are going to be squares. So right here, oh, look at that. There you can see the square. And then we are going to have an infinite number of squares that are infinitely thin, and it's going to make a 3D solid like so. You'll notice, so this is like the roof, right? This is our Google Earth view. This is our street view. You'll notice that this square here is short. Like, see how there's ebbs and dips like waves in the roof? Well, that's because if I unfill it, if we go back here, look at the distance. If we're here, the distance between the upper function and the lower function is less than, say, over here. The distance between the upper function and the lower function is greater. So if that's the base of a square, then of course coming out toward you, like so, that's going to be a much taller square than if we go, whoops, and then if we go like right here, that's a shorter square. Okay? Well, that's fun. Yeah, this one gives us both the Google Earth view, like looking down from the top, and the street view here. Okay. So this one is, what are we looking at? Let me scroll up a bit. Equilateral triangles. Okay, so this is equilateral triangle. So of course the distance from here, because now you can see a very nice looking equilateral triangle from that angle. I can show the slices. So let me go down here. This is cool. Here I'm showing 6 slices. So you can see 6 equilateral triangles, right? And if we increase the number of slices, then we're going to create that 3D solid. 23 slices, 40 slices. So we want to add up an infinite number of triangles that are infinitely thin to create this solid. And in order to add up an infinite number of things, we use calculus.
Okay, so how does this work? Well, there's a formula. So to find the volume, if you have a known cross section, you simply need to find the area of one of your cross sections or one slice, and then you do the integral from A to B. So this is how you're adding up an infinite number of slices that are infinitely thin. So in this diagram, you can see these, I think, are supposed to be isosceles right triangles, and that would be one slice. And if you have an infinite number of slices that are infinitely thin to make your 3D solid, then you want to add up all of those different areas, and then that's going to give you the volume. Notice, since we've already done area of discs and washers, the disc and washer method, that there's no pi. So we saw pi in those other formulas for disc and washer, and of course nothing is squared because again, these are not cylinders. And this formula is only if you're perpendicular to the x-axis, or also known as parallel to the y-axis. If we were parallel to the x-axis, then it would be a different process. So this is just saying that discs and washers are special cases of known cross-sections where the cross-sections are circles. So this is what we were doing before, and this is sort of another view of them. Of course, you're only looking at the top half of the circles. There would be more, the bottom half of the circles there. Okay, so here's our first example. The base of a solid is the region enclosed by this parabola, and y equals 0. The cross sections perpendicular to the x-axis, and we're only going to be doing perpendicular to the x-axis in this video, are squares. We want to find the volume of that solid. So first, it's always a good idea to sort of draw the two-dimensional shapes of the Google Earth view, if you'd like. So this could be my graph. We have a parabola that opens down, and then y equals 0. So the area that would make up the base of my cross-section is this area right here. We need to find these points of intersection where this parabola crosses the x-axis, so those are your x-intercepts or your zeros. And you can find them simply by setting your parabola equation equal to 0. And we get plus or minus 6. So this is negative 6 comma 0, and over here is 6 comma 0. So remember, one slice is going to go from that top of that, from the parabola down to the x-axis there. So if I were to try to draw this in 3 dimensions, which I'm going to try, and then I'm going to erase it because it's going to be sloppy. That's supposed to be a square that's coming out of the screen toward you in 3 dimensions, if you will. I'm going to erase that because it's not very nice. It always confuses me when I try to draw in 3D. This is a square. One side of the square is equal to the upper function minus the lower function. So in this case, our upper function is the parabola, negative 1/9 x squared plus 4. And of course, the lower function, that's just your y-axis, your x-axis, so it's just y equals 0. So that's part of the issue, is figuring out the length of one side of the square. Now, area of a square, so our area function, you know, area of a square is just one side squared. So in this case, we're looking at negative 1/9 x squared plus 4 squared. So that means that your volume formula is going to be the integral from negative 6 to 6 of your area, negative 1/9 x squared plus 4 squared dx. And that works out to be 512 fifths, or approximately 102.4 square units. Or maybe it's exactly, not sure. Over here, I'm showing you what that 3D shape ends up looking like. So again, this right here would be the Google Earth view, and then this over here, the 3D view, that's like your street view. So if you'd like some steps, then we're looking at first, you're going to want to sketch the graph. You need to find the points of intersection for the area that's bounded. The base of the shape, so think about the base as being like the floor, whether it's a square or a rectangle or a triangle, etc. That's going to always be your top function minus your bottom function, or your upper function minus your lower function. Then you want to determine the area of one cross section. So here are some reminders of formulas for areas of some of our shapes. And then you find the volume using this formula. You're just going to do the integral of the area. Let's take a look at another example. The base of the solid is bounded by the x-axis, x equals 9, and y equals the square root of x. The cross sections perpendicular to the x-axis are rectangles whose height is half the base. All right, let's draw a sketch. Okay, here's my sketch. And then the area that would create the base of my solid is this area in here. So let's think about a rectangle. So for a rectangle, we know the area is base times height. Now it says here that your height is half the base. So we already know that the height is half the base. So really our formula is not going to be base times height. It's going to be base times 1/2 times the base. Or in other words, 1/2 times the base squared. I really should call this area. And that equals the rectangle, equals the area. Now the challenge is that we need to figure out what's the formula for the base of our rectangle. Now it says the base of the solid, it says right here, the base of the solid is this region bounded by these situations. So the x-axis, the curve, and the x equals 9. So our rectangle base is going to be that distance from the curve down to the x-axis. And then you're going to have this rectangle sort of coming out of the page toward you. So that's simply going to be the upper function, which is the square root of x, minus the lower function, which is just 0, again in this case. So for our area function, that's going to be 1/2 times the square root of x squared, right? Because we just said that the base was the square root of x, so just substituting that in there. Square root of x squared. Of course, that's just going to be x squared, right? Sorry, that's just going to be x. So it's going to be 1/2 times x, which makes your volume the integral from 0 to 9 of that function, 1/2 x dx, which is equal to 81/4. And on this slide, I'm showing you the street view. Sorry, this is the Google Earth view, so looking down at the top. And then this is the street view. So you can sort of see these rectangles whose height is half of the base, and they're getting shorter and shorter as you get closer and closer to the origin there, where the distances, the bases are short. All right, our last example. Find the volume of the solid whose base is the region bounded by these lines. Sorry, it says lines, should be curves. Y equals 1 minus x squared, y equals 0. The cross sections taken perpendicular to the x-axis are isosceles right triangles. Let's draw a picture. Okay, here's my curve. Now, what I notice is that, let me go back and read it again. It says the volume of the solid whose base is the region bounded by the lines, which again should say curves, 1 minus x squared, and y equals 0, so that's the x-axis, if the cross sections are taken, are isosceles right triangles. So let me sketch in the area that's the base, so that's going to be this region here, the base of my isosceles right triangle. Let's think about a right triangle. An isosceles right triangle is essentially something like this, right? It's going to be like, the two legs are going to be the same length. So the area is 1/2 times the base times the height, right? We know that formula from geometry. But since the base and the height are the same, we can really say that's going to be 1/2 times the base, or 1/2 times the base squared. So it's basically just like the other problem, except we have a different shape here, okay? So we need to think about the length of the base of the isosceles right triangle. Feel free to pause the video and figure this out on your own. But the base of the right triangle is going to be that distance from the parabola down to the x-axis. So again, we're looking at the base being, in this case, 1 minus x squared minus 0. So then the area of the triangle will be 1/2 times 1 minus x squared squared. So then the volume will be the integral from, oh, we forgot to mention what these points of intersection would be. Well, you can easily figure out this is going to be a -1, 0, and this one is at 1, 0. So your lower bound is -1, your upper bound is +1, and then it's going to be 1/2 times 1 minus x squared dx, and that works out to be 8/15. And on this slide, you can see the three-dimensional shape that's created. And of course, that's your street view over there. And then this is similar to what I drew. This would be your like Google Earth view. Have a great day.